And again, in geological space, we use some of these reactions up to 1,000 degree temperature range. Okay? So here's the natural, 1,000 times the natural log alpha turns out to be very close to, well, a large separation that's very close to the per mil notation, the per mil difference between things. And so these are just the isotope differences between liquid and vapor water, calcite water, CO2 water over a 40 degree temperature range, the temperature range of interest in ecology and low temperature geochemistry. And we can see what this is in the 1 over T space, which has the same form as the Clausius-Clapeyron equation. These are actually straighter lines than this, although it doesn't look like it. But if we extended this over 1,000 degrees Celsius, these would be straighter lines than those. Not a big deal. Okay? But so this is the sort of the per mil difference in our temperature space. So for calcite water, this is 35 per mil versus 25 per mil. We can measure that very easily. In water, for hydrogen, we can see that the isotope difference is about 10 times higher than actually for carbon and oxygen. But again, we remember that the mass difference is about 10 times higher for hydrogen than it is for hydrogen-oxygen. This is 1 part in 1, and this is 2 parts in 20. So it's a difference of about 10, and that translates to this. So we get very large isotope separation for these hydrogen-bearing species. Okay, now here's where I just want to make sure that we get on a little bit of the same page. Okay, this alpha, this isotope fractionation, is for species that are in isotope equilibrium. Okay? And another parallel term, and I'm just going to say, and this is in geology and oceanography. Okay? Isotope enrichment is epsilon, is just alpha minus 1 times 1,000. So again, this is what that looks like. We call isotope separation, or big delta, if we just subtract these two isotope values. And we call that capital delta AB. And this is what geologists have. And this is because it turns out that 1,000 times natural log alpha, 1.00x, is about equal to x. And this is really handy. Okay? Now, about 30 years ago, I think it was when it became real easy to analyze samples. The biological community developed a parallel terminology. Alpha was equal to A, ratio A divided by B, but not in isotope equilibrium. So it's just comparing two things that may or may not be in isotope equilibrium. And then the term was developed and called isotope discrimination, is this alpha minus 1 times 1,000. And notice that this is different than that formula. Okay? And so the form, it's identical to this formula. But it's really important to realize the distinction between if something is equilibrium or not. Okay, and what's really important is to realize these two parallel definitions. I've seen papers where people have used both definitions, but for the same symbol in the same paper, and they're not the same. Okay, and so this is a mistake you shouldn't make, especially not if it's in a paper that I am reviewing. Okay, now why do this? I'm just showing you the calculator that was used a long time ago. Probably none of you have a calculator that looks like this. Does anybody own a calculator that looks like this? I mean, you may have seen your parents or grandparents may have this kind of calculator. I love these. But and Harman Craig in 1954 pointed out that this capital delta, where you subtract one value to another, should only be done if the delta value is less than 10 per mil. Okay? Now, in most isotope systems, that's about what it is, except hydrogen. Okay? And I see papers where people are making this difference in hydrogen, and it is like a 10 per mil mistake by the time the isotope separation gets to be 100 per mil, which it happens easily in a hydrogen system. It's a 10 per mil mistake. Okay? And that's a big deal. Okay? So please don't embarrass yourself by doing this. And I'll just illustrate this with this nice table, which is basically just shows these the geological definitions, and we're just going to look at delta values for phases A and B, okay? And these are the theoretical fractionation factors, and 1,000 natural log alpha is a value of 30.46, and the isotope separation, just the big delta is 30 per mil, and this isotope enrichment value is 30.93. But you see this value, which actually is the same, is the same as that. This capital delta is 30.93 in the biological definitions, but capital delta in the geological definition is only 30 per mil. So that's a 1 per mil difference over 30. And like I say, this problem just gets worse as the number gets bigger. Okay? So it's important to define, if you're using any of these terms in a paper or something, make sure they're defined, because the two different literatures have parallel definitions for the same symbol. And certainly never use the same symbol for two different definitions in the same paper. And like I say, I have seen that happen. Oh, and the other thing is I've seen is, yes, people have done this and not realized that it's an approximation and written a whole paper on how the isotope effect is scale dependent, not having realized that in 1954, Harman Craig said, never ever do this. And here's just a classic example. There's two different isotope references that are used in the oxygen system. The oceanographers for carbonates tend to use PDB as the standard. And I'll talk about standards slightly different. SMO is used as a oxygen isotope standard in different things. Depending on which is your standard, this actually, capital delta AB, is a per mil different. Okay, so it's a scale dependent. So again, this approximation is useful if you know what you're doing, but never use it in calculations that are further used.